speaker. He's from Fujitsu Laboratories, and he's talking about hippocampal formation mechanism will inspire frame generation for building an artificial general intelligence. And that looks like a really interesting topic to me. So I'll say hi to Dr. Yamakawa.
Oh, it's okay. I started now. Thank you, Mr. And good morning, everyone. It is my great pleasure visiting beautiful city, and this opportunity presents such a nice conference. Today's first setting of my goal, I propose the singularity factor at first. My challenge today is decreasing 5 years of this factor. Now I come back to the main subject. Hippocampal formation mechanism will inspire frame generation for building an AGI. Before outlining my talk, here's about my company Fujitsu, which is the third largest global IT company, service vendor. It sells the IT solution, personal computer, supercomputer, and so on. For making this a breakthrough, we hope to understand computer and achieve the brain function, such as creativity, intuition, and AGI. Related to this vision, we are also interested in the singularity. Therefore, we have co-organized a symposium titled "The Future of the Human Intelligence and Computer Science" in this September. Then I have divided the talk into 4 parts. First, I contend that the autonomous frame generation function is important for technical element realizing AGI. And second, to learn something about the frame generation for the brain, I focus on the regions of interest. And third, I will then propose distributed equivalent groups as a plausible relation representation in the brain. By the end of my talk, I hope you will find that to approach AGI, frame generation by variable assimilation process can be explored by using distributed equivalent groups. Now, let us move on to the main subject. Needless to say, intelligence are based on the inferences. For approaching AGI, I'm sure that inference process should be reconsidered from the broad perspective. In general, frames can be seen as the source of the empirical inferences. Here, the frame is a popular declarative knowledge representation. It is combined of the set of variables, and each variable has value for every event. Then, an AI system must use frame for the facing tasks. For narrow AI system, human can design an appropriate frame beforehand. But AGI system must automatically adapt to the various tasks and situations like the human brain. So, the ability to generate a new frame is indispensable for the AGI system. However, today's machine learning tends to focus on the calculation method for given frame. Then, I have next question is how to make the frames. If there are a lot of frames already, variable assimilation process that combine the existing frame are plausibly nice way to perform frame generation. In this process, partial variables are set of 2 original frames are matched up using the structure of the relations. In this example, a relation between variable A and B is original frame 1 is matched up with a relation between variable E and G in original frame 2. Basically, this idea is similar to an early study in the cognitive science, which is the structure mapping theory proposed by Jetland in 1989 to explain the process of analogy. But symbols are used to represent relations. So there's no way of avoiding the knowledge acquisition bottleneck. As animal can do, the system should autonomously run the sub-symbolic relations among variables to generate a new phrase. Now, imagine the inside of your brain, such as the neocortex, cerebellum, hippocampus, and so on. You can observe many but sparse signals running through a large-scale neural network. By regarding the activities of the neurons, by regarding as a neuron or columns as a variables, the brain intrinsically contains large frames of neuronal variables. For processing sparse sequential data, and then obviously human brain have variable assimilation ability to realize high-level cognition, such as the visual object recognition, analogy, and transformational creativity, and so on. But I believe that many of animals also have this kind of ability, such as spatial inferences. For example, animals can transform from the egocentric coordinates to the allocentric coordinates to perform the navigation. In the brain, the relation must be represented in a sub-symbolic way. Now, I focus on the brain region to get some hints for frame generation. For some reason, the neocortex is the most likely candidate for the brain region that can store frames and activate them. Main reason is the uniform neural architecture suggests the general information processing. And please look at the other three reasons on the paper. If the neocortex is the brain region for accumulating frames, it is natural to guess that the frames also generated in the field. However, I contend that the neocortex cannot execute variable assimilation process all by itself. For the variable assimilation, relation among variables must be compared frequently, but neocortex does relation in distributed manner. Then the dense communication beyond the region is necessary in neocortex. However, there are not any enough dense neural circuits which connect beyond the region reciprocally. Then the neocortex cannot globally execute a global variable assimilation beyond the region. Instead, I assume that hippocampal formation is the brain region most probable for the generating frames. There are four reasons. First, the hippocampal formation receives a projection, neural projection from a wide area of the neocortex. Second, the hippocampal formation memorizes experience before the neocortex and transport them later, and other reasons. For these reasons, we assume that frame generation process supported by the index of relations in the hippocampal formation. Then the next question is how to represent the sub-symbolic relations in the hippocampal formation. Now, as a representation for sub-symbolic relations, we introduce a distribution equivalent groups, which we call DEGs. Here, there's a partial sequential event pattern within the multidimensional subspace in consideration of variable exchange symmetry. This representation is assumed based on two specific features of the hippocampal formation. Partial sequential events are assumed based on the phase precision phenomenon. This phenomenon brings about 10 sequential events together within the theta rhythm. And multidimensional surface assumed based on the configural association theory. This theory insists that the hippocampal formation associates a combination of stimuli rather than individual stimuli with the meaning of the behavior. Let me explain how to extract the DEGs from the frame. As the left box indicates, this frame contains 4 binary barriers A, B, C, and D, and contains 5 sequential events, which can select arbitrary combination of partial event sequence and variable subset as DEGs. However, I explain just one instance from various cases. Please look at the center box. 2-dimensional DEGs were 3 events, which 3 events were extracted from the frame. This DEG selects 2 variables A and B, and this DEG includes the events 00, 10, and 11. And in the brain, neurons can't easily distinguish by their activities. Therefore, we introduce the variable exchange symmetry to ignore the identity of the neurons. The right box indicates the factorized DEG pattern depending on this symmetry. In this figure, I described a primitive variable assimilation process. As in the previous slide, this DEG is upper DEG is extracted from an original frame 1. In this case, same DEG pattern is extracted from original frame 2, which led to variable ERG. Then we recognize that the relation between variables A and B is the same as the relation between variables E and G, because they share the same DEG pattern. As shown, the variable assimilation process is basically accomplished by the shared DEGs. Then we can list all the DEGs pattern for binary 2-dimensional case. There's only one pattern with no event, and there are 3 patterns for one event, and this center pattern has a symmetric pair. Here is the pattern, in the red circle. Here is the pattern was explained in the previous slide. The last issue of my talk is this 12 pattern enough to categorize the combination of the thousands of variables? Because DEGs are used as relation for categorizing the combination of variables. DEGs should have a diversity comparable to the total number of the subspace. Please look at this graph figure. Horizontal axis indicates size of the subspace D, number of DEGs pattern, and total number of subsets are compared. In detail, blue curve indicates number of DEGs patterns. There are 12 DEGs patterns for 2-dimensional DEGs, as explained in the former slide. On the contrary, the orange line indicates the number of subspace for the 100,000 variables, and a pink line for a million variables. Here, number of variables are corresponding to number of excitatory neurons in the hippocampal formations. As you can see, total number of the subsets are caught up by the number of 8-dimensional DEGs patterns. This is red line. This is because number of DEGs patterns increase almost like second-order exponential function with the size of the subspace. As a result, 8-dimensional DEGs can categorize the subspace in the hippocampal formation. It means that the DEGs can support variable assimilation process. Let us review what I mentioned today. Frame generation will help building AGI. And variable assimilation process are promising as frame generation. And distribution equivalent group will support variable assimilation process. Finally, I give some implication of my talk. Because DEGs are subsymbolic, we can explore various algorithms for substantial data that need relations. Furthermore, new possibilities open up to construct biologically plausible neural model or cognitive model which needs subsymbolic relations. I believe that this effort is a step in the almost right direction toward AGI. Then, in the future, I'd like to introduce frame generation with using DEGs to some algorithms, such as deep learning, Bayesian network, and so on. And of course, we have a choice to consider sequential equivalent groups instead of DEGs, because set of events in the brain begin with a sequence. Thank you for listening.
We have a few minutes for questions. Are there any questions, guys? So I'll bring you the mic.
It's more for clarification than as a question. Am I right in thinking that what you're suggesting is that what's happening is that the inputs, multimodal inputs, are being decomposed or compressed into these DEGs by the hippocampus, and then these are being stored within the neocortex?
I can catch your question, but your question is...
Am I right to think of the DEGs as being a compressed form of the inputs that are coming in? And this compression is taking place in the hippocampus?
I don't assume that DEG is a compression. That's a kind of representation relation, I said. So, compression is another matter, I think. Can you get the answer?
Other questions?
How do you think the search problem of finding these sets of variables in different DEGs that can be identified with each other might be solved?
After this step, you mean?
Well, once you have, there's the variable, the key variable assimilation step is finding that two sort of different groups of variables exhibit the same DEG. But how? I mean, that seems like an exponential search problem. How do you find those identifications?
I think your question is search process is kind of finding the matching relation.
Right.
Yeah. It's I don't think say about this kind of thing today, but it's obviously significant and we have to code it. But that kind of technology is. Some part studied in the, as I said, the structure mapping theory and something research in the analogy. So we can get some hints there. It's not so special technology. But I think the point is finding good relation at depth we use this DEG. Of course, 2 and 12 is too small, but it becomes too big for if it's 8 dimensions. So we have to choose some useful DEGs to categorize as a relation. So that kind of problem may be the problem for this method, I think.
I'm going to throw in a question of my own, if you don't mind. mind, I'm going to pretend to be Ben Goertzel for a second. Because, of course, his question would be, well, we're trying to show how neuroscience here really relates to AGI and how it's important. So one of the things that you mentioned as a major reason why this needs to be done is because you need to be able to provide connections all throughout the neocortex to get from one region to another. Now, in the case of an AGI, an AI system, where you have access to all of the memory through a memory bus, what, is this how you would have to do it?
It's my strategy of my research. Of course, if the principle is always no, we don't have to trap in the brain mechanism. But if we go thinking something with the brain, we are easy to get hint of something, information processing. So this is for one example that I have learned from brain. This theta precision is very famous in the hippocampus. And I imagine the 10 sequence events encoded is some kind of package, is maybe the hint for thinking about the representation. That kind of thing is occur if we think like brain GUI. So this is my research strategy.
Okay, thank you very much.